I'm now going to look at color management and profiles. So everything that works with color has deficiencies and inconsistencies. Nothing can be made perfect. So profile is a digital file that describes the way a particular device works with color, applying a correction factor that the computer is able to use to maintain consistent color throughout the digital workflow. So color spaces and profiles are all like digital tags attached to the file, and for the sake of this demo the terms basically mean the same thing. So why do we need profiles and what are they? Okay, so let's just have a look. When we have no light, everything is black. Okay, and we have three primary color channels: red, green and blue, to give us our light. When you mix them together, we get this sort of effect. Red, green and blue mixed together in equal quantities gives us pure white. Then we have the complementary colors of cyan, magenta and yellow in between the three. And this is what we call the additive color system, because we're dealing with light adding to light adding to light, which is different to the painting system, which actually reduces light every time you add a pigment. So this is an idealized color system. However, no light source like the sun, a light bulb, a monitor or a receiver, the thing that actually detects this light, like the human eye or a digital camera, nothing responds in such a perfect way. So anomalies in the way each color channel, the red, green and blue, is handled inevitably results in color casts unless corrections are made. Profiles are corrective adjustments made to color data, compensating for these known anomalies. So if we have a quick look at the red, green and blue again, full red, green and blue will produce white. 50% red, green and blue will produce a grey rather than white, because there's only 50% of the amount of light. So we perceive that as grey when we're looking at a full 100% red, green and blue. We then perceive this as grey. 25% of each one will produce a 25% grey. Okay, you get the idea. But the idea is that if we have an equal balance of red, green and blue, at different intensities, the resulting blend will be grayscale, either from white all the way through to black, but each one will be a different shade of grey in between. So varying but equal amounts of red, green, blue gives us a complete range of grey tonal range. So if the greys are correct, any colours should also appear correct. So if we have a look at this puffin and we apply a red, green, blue, cyan, magenta, yellow color cast. So we've still got red, green and blue, red, green and blue, red, green, blue, but there's a bias of red, a bias of green, a bias of blue, bias of cyan, okay, and we perceive these as color casts. Okay, it doesn't look right because the lighting is incorrect, and this could occur on your monitor. Your monitor could be giving the wrong colors out. Your camera could be capturing the wrong colors, the wrong balance of colors. So this is why we need to correct these. So if one or two of the RGB colors are disproportionately represented, then the image will appear to have a color cast. So the camera has got red, green and blue sensors, and it captures like monochrome versions of red, green and blue, or luminosity. So it's red luminosity, green luminosity and blue luminosity. That's how it captures the light on its sensors that are dedicated to those colors. So if we just add a color, just so it can remind us the actual color channels that we're looking at. So the ideal response, if we had an ideal camera with a sensor looking at the red channel, the red information in the picture, it would start off at black, nothing, no red, and it would go through all the different shades of red through to really bright red, the brightest red it can respond to, in a linear way. So there wouldn't be any ups and downs in this response. It would respond to the full brightness range of reds in an absolutely positive linear way. Same with the green. And this is the ideal response. This is what we hope for. But of course, when they come to manufacture these sensors and the filters that they apply over the top of the sensors to respond to the different colors, we may find that the response doesn't behave in a linear way, but in a predictable but inconsistent way, like this. So each sensor, each red sensor, would have the same problems inherent in it. Each green one, the same problems. And you can see that they could all be different. But the manufacturers should be able to calculate what the problems are. Okay, and then here we go. So this is what they've deduced. We've got a problem with the red sensor, it does that. Problem with the green sensor, it does that. And the blue sensor, it does that. So they can create a software patch that compensates for these irregularities. And that software is a profile. So what comes out at the end, even though we've got a problem with the sensors, this is just an example, even though we've got a potential problem with the sensors, the resulting output, by understanding what the problems are, can produce a software patch and then have an output that equates to the conditions of the input. Okay, so we get consistent color data to the computer. So this is an example for the camera sensor. You'd have equal problems with a scanner, with a monitor, and each image has got a color profile attached to it. sRGB, ProPhoto RGB, Adobe 1998. Those are like profiles that describe to the computer how the color information of that image needs to be presented. So those are, well, that is how, that's what profiles are all about.